So I assume people can hear us online. All right, good afternoon, everyone. So I'm really happy to introduce Professor Trisha Sain, who is currently an associate professor in the Mechanical and Aerospace Engineering Department at Michigan Tech. She's been there since 2016. Trisha received her PhD from Indian Institute of Science in Bangalore, India. She then did a postdoc at the Universidad Politécnica de Catalunya in Barcelona, also known as Barcelona. And after that, she did a postdoc here in the Aero department and the ME department, working for Tony Wass and myself. So her research focuses on understanding the behavior of advanced engineering materials, including multi-scale and coupled physics behavior of polymers and polymer composite materials, fracture damage and impact behavior of materials, degradation of metallic material in extreme environments, and aging behavior of recyclable thermosets. Today, she's going to talk to us about modeling fracture in fiber reinforced composites, a phased field approach. So welcome, Trisha. Welcome back.
Thank you. Thank you, Ellen, for hosting me. And it is always a pleasure to come back, which we call as home. Because I started my academic journey in the United States being in Ann Arbor. So it's always a strong sentiment for me when I come back to the campus. So I will talk some of our recent work focusing on modeling fracture in fiber reinforced composites using a phase field approach. So FRPC, which is the short acronym for fiber reinforced polymer composite as a material, many of you probably are familiar, is widely used in aerospace and many other critical engineering applications because of their very beautiful properties such as strength and toughness, precisely when we normalize these properties against their weight or specific properties are really remarkable compared to their metallic counterparts. But everything comes at a cost, so it's not all good when we look into the fracture mechanics behavior of these materials. The complexity arises from the underlying micromechanics involving matrix cracking, fiber breakage, fiber matrix debonding in the lamina level. And most often these composite materials are used in laminate forms, where basically individual plies of single fiber orientation are stuck together like this. And then the interface between two successive lamina also promotes some failure mechanism called delamination. And most often this interlaminar fracture or delamination interacts with this intra or bulk level fracture mechanism, depending on, of course, the ply arrangement, external loading conditions, and the properties of individual constituents such as the fiber volume fraction, the matrix viscoelasticity, etc. So in the modeling domain of this complex fracture behavior, of course, characterizing and incorporating multiple damage mechanisms is always a challenging problem in the composite community. More precisely, the interactions between intra to interlaminar cracking has been reported as a big challenge. And those of you are familiar a little bit in the fracture of FRPC, you probably have heard these two keywords, cohesive zone modeling or continuum damage mechanics approach. Both have been used widely to model cracking behavior in composites. Now, each of these methods has their own advantages over disadvantages. For example, cohesive zone modeling requires the description of the cohesive zone a priori to the propagating crack path. So if we know the crack path beforehand, then we can define the cohesive zone along those paths. But if we do not know a priori which way the crack will propagate, then it demands that we have to prescribe the cohesive zone model for the entire domain and becomes quite extensive computationally. So our objective in this project was if we can develop a computationally efficient and accurate model that is capable of all these complex features describing the fracture behavior of fiber-reinforced composites. And for that, we will use phase field fracture method. So I will come in a minute why phase field fracture, particularly to solve this problem. Prior to that, let's talk about very quickly a quick introduction on the unidirectional FRPC constitutive behavior. So as you can see here, it's a schematic representation. So the unidirectional FRPC, or in short form, we call that UD-FRPC, their stress-strain response depends on the fiber orientation with respect to the loading axis. Okay. Similarly, if you see the fracture behavior, and by the way, this experiment was done here in University of Michigan in Professor Wass's lab, where basically they considered open hole tensile sample with fiber oriented at different angle with respect to the loading direction, and these are open hole tension, so the samples were pulled along horizontal direction. And you can see the crack starts from the notched edge and then propagated following the fiber path. Okay, so highly anisotropic phenomena even when the external load was purely tension dominated. So characterizing that and incorporating that in a modeling environment has been challenging. Of course, cohesive zone model has been used as a recourse, but there were issues. So we are trying to handle some of them through this phase field approach. So before going to the phase field description of fracture, very classical inception of fracture mechanics started with Griffith's theory of fracture, which basically states a condition of when the crack will grow in a linear elastic brittle material. And it gives basically energy balance sort of statement to determine that criteria, which states that when the elastic energy or the stored strain energy released per unit area of crack equates the material's fracture resistance, or formally known as fracture toughness, then that determines the unstable crack growth criteria. And this was very simple and widely applicable to describe the fracture behavior of brittle material. And of course, based on that Griffith's seminal work, there have been a significant volume of work in fracture mechanics because it's challenging to deal as the material constitutive description changes from brittle to ductile, then heterogeneity and isotropy, etc., etc. So I borrowed a famous quote by Professor Bazal that, like turbulence, fracture mechanics is different. This formidable subject has been researched for a century and probably will be for another, because there are still quite a lot of unresolved issues. One of them is if we just model the crack as a sharp discontinuity, that is what it is actually. In reality, crack forms as a sharp discontinuity, and those of you are dealing with continuum mechanics, you probably know that all our equations in continuum mechanics based on a critical assumption that everything is continuous. So our displacement field and strain and stress, everything is continuous, and we have a very easy solution scheme, energy minimization. But the moment there is a sharp discontinuity forms, then those assumptions become invalid, and we have to do special treatment to represent those discontinuity and still work in the realm of continuum mechanics. So people have been doing that. It's not that it was challenging, so nobody used that one, but we are trying to get another alternate path of representing crack instead of a sharp discontinuity, if we can represent that as a regularizing or smoothening approximation. And phase field framework of fracture actually lies in that domain of fracture modeling. Okay, so smoothening the sharp discontinuity, that's the core idea of representing sharp crack through phase field. So now jumping into the core description or the theory of phase field, which basically started as formally variational theory of fracture, and the seminal work was by Frankfurt and Marigo in the late 90s, who recasted the Griffith's statement of energy balance in the form of energy minimization. So if you can write the total energy of a cracked body, which contains the bulk or the bulk stored elastic energy, and then a fracture energy term, which is balanced with the external work. And then if you can minimize this energy somehow, then you can actually, the crack path, the propagating crack path emerges naturally from the solution of this minimization problem. Okay, so the two key points that we need to focus here, of course, remember the fracture energy is described over the crack surface area, whereas this bulk elastic energy is integrated over the volumetric domain. Okay, so it's basically one over the surface energy, one over the surface area term, and this one is the bulk volumetric term. Okay, so theoretically it was possible, but numerically it was quite challenging to implement until this late 2000 work came up. Okay, where the description of this order parameter, which is more formally known as order parameter in the broader domain of phase field approximation, basically was introduced to describe the damage field. So a sharp crack is represented by this. If you just compare equivalent damage description of a sharp crack, then at this x-axis, at x equal to 0, we have d equal to 1, which is a completely damaged or cracked material, and everywhere else d is 0. So that's the sharp representation. But in the domain of phase field, we approximate this by a smoothing of this d variable. So instead of the sharp jump from 0 to 1, we describe this jump over a length scale LC, and this jump is very smooth. Again, the description of d equals to 0 is uncracked and d equal to 1 fully cracked material holds true. But the only difference is now it's a smoothened approximation, which is controlled by this length scale parameter LC. This is a very important characteristic parameter in the domain of phase field fracture. Now, by the introduction of this smoothing phase field variable, we can further approximate this fracture energy, which was originally crafted over a surface area term, now integrated over a volumetric domain. And how do we do that? We basically introduce something called a crack density functional. You can just think of like a strain energy density functional. Okay. Now, in the crack density functional, this gamma depends on both the phase field variable d and its gradient term del d. So that gradient controls how sharp that changes from d equal to 0 to 1 is going to happen. And that control can be done by the choice of your length scale parameter. Okay, so we basically come up with this crack density functional. So there are certain approximations available again in phase field literature. These are widely used, that you can take this this homogeneous form of the D, and there are two typical choices possible. These were borrowed, by the way. These are not crafted solely for the phase field domain. These are borrowed from image segmentation literature, essentially. So you can choose typical form of this homogeneous part of the damage, and then eventually, basically the whole idea was to make this surface area integral to a volumetric domain. Okay, so once we have that, then in the total energy term, everything is over the volumetric domain now. So we can minimize this energy by simple variational principle to solve for not only the displacement field now, also for the damage field. So the damage field propagating crack path essentially emerges as the solution of this minimization problem. Okay, and of course, along with that, this implementation further demands criteria like the damage is irreversible. Okay, so no healing is possible once the crack is happening, because we are not solving any dissipation inequality here. It's just energy minimization. So there is a possibility if we are doing an unloading, the crack can go and heal. So we have to impose this constraint from outside the additional principle. Okay, so this was the core of this phase field fracture theory. Now we tried to extend the classical phase field theory to model fracture in FRPC composite. That was our sole motivation. So along with the sharp crack approximation, remember, as I said before, that most of these fiber reinforced composite materials are used in laminate forms, and these laminates often have off-angle lamina orientation. So they have fiber orientation mismatch, and that mismatch actually gives rise to this interface. So even without any crack at the interface, just because of this mismatch of fiber orientation, there is a displacement discontinuity along those methane surface. Okay, so any sharp discontinuity again troubles our continuum mechanics approximation and the solution. So what we did is, just like the phase field approximation, we used another smoothing scheme to smoothen out these sharp interfaces. So we had D priori to describe the sharp crack. Now we have beta, which is also a phase field variable. The difference between D and beta is that beta does not evolve with time. So it's a fixed scalar smoothing variable, which varies again between 0 and 1. 0 represents the bulk material, 1 represents the sharp interface. So if you just think of ideal schematic of this smoothing phenomena, so you have a sharp crack in the domain and you have a sharp interface, both can be regularized by introducing the phase field variable D and beta and associated length scale parameter. Okay. So with that introduction of beta and D, now my total energy in a regularized form for the domain can be written in this. So if you just compare, these two were surface term. Again, the fracture ideally supposed to be on a surface area term, and the interface was also a surface area term. But because we have this regularized approximation, we can craft both of these terms in the volumetric domain. Okay. And then if you look at here, the two important parts, we have this 1 minus beta x term sitting in this fracture dissipation term. So this, what does this do? This is basically controlling the interactive crack propagation between the interface and the bulk. So if beta is 0, then you are actually in the bulk. So correspondingly, GC will be the bulk fracture energy or the laminar level fracture energy. And beta is non-zero, GC will be the interfacial fracture energy. Okay. And because there is this damage happening at the expense of stored elastic energy, so as the damage propagates, you lose the stored elastic energy. That is taken care of by this so-called degradation function, GD, sitting on this elastic energy term, right? So as D increases, GD increases, and GD decreases, and your elastic strain energy, stored elastic energy, keeps dropping. So the material loses stiffness. And in the interface regularization, just pay attention that we have a very similar regularization term, just like the damage I showed you before, okay, which depends on the beta as well as the gradient beta. Okay. Now, introduction of this gradient term in both this case makes this method, phase field method, non-local. So it doesn't depend on the mesh. Okay. Those of you who have worked in continuum damage mechanics, you know that very similar framework is used in continuum damage mechanics approach also. But the problem there is all the results are mesh sensitive, classical damage mechanics model. So if you make your mesh finer and finer, then it converges. But for every study, you have to do that mesh sensitivity analysis. But just because we have this gradient term taken into account in the formulation, by itself, by construction, this method is mesh insensitive. Okay. So with this framework, now the major important point is, again, I'm bringing back those experimental pictures, that the crack is heavily orientation dependent, fiber orientation dependent. So I'm pulling both of these specimen under tensile loading, but in one case, the loading is parallel to the fiber direction, and another direction, the fiber is an off angle, 45-degree angle, and the crack propagation is happening parallel to the fiber direction. So how to incorporate this anisotropy in the fracture? So for that, what we did is, so this was the typical crack density functional incorporating a homogeneous damage field and a gradient of the damage field. That gives an isotropic crack growth very nicely. And it's very well known in the literature. It's like the early study of phase field crack growth. So what we did here to begin with was we introduced an anisotropic tensor in the gradient term. And if you look closely, the anisotropic gradient term essentially have a scalar variable omega, and this dyad, the tensor, essentially represents the fiber planes. So AR gamma is the fiber orientation vector. So all it says is that if the gradient tries to align parallel to the fiber direction, then we have a higher energetic penalty. So it will try to align the gradient orthogonal to the fiber direction. So it will align the crack growth along the fiber direction. So if we do that, then we can write of course, now the regularized fracture energy has an anisotropic form, right? And if omega gamma is 0, then you actually get back to the isotropic form of it. So this was for the anisotropic crack growth. Then in the interfaces, of course, there is no anisotropy here. And as I mentioned before, this is just static. Once you have it, it doesn't evolve, okay? But it's just the smoothening interface. There is no, yeah, go ahead, please.
The elasticity remains isotropic though, right?
No, not yet. I have not gone to the elasticity. I will tell you what's the constitutive equation. No, it cannot be isotropic.
Because if it's
If there is a strong alignment preference, it cannot be isotropic.
Right.
I'll show you in probably next 2 slides. Just on there. So, okay. So that was the interface description. Then, in addition to that, if you remember in the free energy expression, I think 2 slides before, I did not explain it here. So the interfacial free energy classically is expressed based on a displacement jump, because as I said, there is a displacement discontinuity along this wetting interface between 2 successive lamina. So this displacement jump used to be the most important kinematical variable, classical theory. So the free energy is expressed as a function of this displacement jump across this sharp interface. Now, the idea that we are borrowing in this phase field framework is that we will get rid of all sorts of discontinuity, sharp discontinuity that is appearing. So to do that, we approximate this displacement jump across this interface. And we do a very simple trick here, just a fast order Taylor series expansion of the displacement field across this neighborhood of this separating interface. And it's fairly simple, but there is a catch here that this approximation involves, because it's Taylor series expansion, right? So it's nearest neighborhood. So we have to choose this distance h over which we are doing this approximation to be small enough so that we do not do a very rough jump approximation, okay? And that automatically comes because, remember what we did, we actually smoothened the interface field also, right? Through the introduction of beta parameter. So we need a smooth approximation for beta anyway that tells us that we need to resolve our mesh fine enough so that this jump approximation remains accurate enough, okay? So with that, basically now what we did, we have a smeared crack, a smeared interface, and the jump across this interface is also smoothened out. So there is no sharp discontinuity in the entire domain at all, okay? Now comes your question, what was my elasticity? So for the constitutive model, in the first part of the work, this is what we have used. So each lamina level constitutive description depends 2 important characteristics. One is the fiber volume fraction and the direction or the alignment of the fiber, okay? So that's the vector representing the direction of the fiber, and this is the fiber volume fraction. In the free energy, it is very simple rule of mixture, which is factored by the fiber volume fraction. The matrix is considered to be isotropic. The fiber, on the other hand, was axially deformable, stretch-dominated component. And this is how we calculate the stretch along its direction, and a simple quadratic form was chosen to represent the fiber part of the free energy. So we can basically fit the material parameters to match the elasticity. So this is what we started. So yes, according to your question, there was an isotropy because we just took axial stretch in the fiber orientation direction for the fiber part of the free energy. So with this very simple constitutive description, we went ahead and applied the variational principle to get into the governing equation. So we have the classical stress equilibrium and of course the phase field equations. So here we have done quite a bit of manipulation. I'm not going into the detail because you can find it out in our recent papers. But again, reminding you about that this 1 minus beta term basically takes care of this interactive fracture phenomena. So if the crack traverses from bulk to the interface and then interface to the bulk again, then this term is going to dictate how the fracture energy will change as the crack path changes. And of course, remember that important constraint that damage cannot heal once it happens. So we used this history function-based approach. There are still some unresolved questions in the phase field approach, phase field methodology of using age-based. That is, age is called the history function-based approach. But for the time being, we are using this one because it is fairly easy to deal with. There are other approaches, for example, Lagrange multiplier-based approaches to introduce this constraint and make it an equality constraint and then solve the whole differential equation. That could be another way. So then, of course, H from the construction itself is the maximum of the history of the elastic strain energy and factored by a term which basically acts as a threshold. And just manipulating the length scale parameter, we can actually craft this model to match the tensile strength of the materials too. Okay, so I'll come back to that detail. But for the time being, once we have the governing differential equation, we have additionally the bulk lamina constitutive, as I just mentioned you, a very simple rule of mixture type decomposition to begin with. And then we have a traction separation law to describe the cohesive interface behavior. But remember, there is no displacement jump. The displacement jump is now a smoothened approximation based on the Taylor series approximation that I just showed you. Okay, so it doesn't require any nodal tracking, how the interface is separating, etc., what you do in classical cohesive zone-based modeling. Completely, you can avoid those completely. And then in addition to that, of course, the method requires that fracture happens only in tension. So you can actually do those type of all sorts of decomposition to ensure that fracture do not happen in compressive loading. If you have a shear-driven situation, then you can actually decompose your elastic energy into deviatoric and volumetric part and then make the deviatoric part driving your fracture, etc. And so with this, some results, basically again, going back to Professor Vasa's experiments to validate some of the prediction that they have observed. So we see our anisotropic, mathematical trick that we did basically captures the crack fiber orientation dependent crack growth in these VHT samples. And I will show you more validations in the coming slides. But we basically tried to see if the interactive crack propagation phenomena can be predicted now. So here we are doing another simulation of laminate structure. So we have two different lamina with two different fiber orientation, and the interface is sitting exactly at the mid plane. And intentionally, we put the initial notch at an offset with respect to the mid plane, so that we see the crack propagation, this interactive crack propagation phenomena. And we did many different case studies. I will show you one particular one. And of course, these are the typical material properties. We studied two restrictive cases. One is when the interface is weaker than the bottom lamina toughness. Another is the vice versa. Basically, the interface is stronger than the bottom lamina. So with that, let's look at some of the results that we saw. So in this particular example, I'm showing you that the bottom lamina fiber orientation is kept as 45 degree. And as I said before, the pre-notch is here. The interface is at the mid plane. And we keep on changing the orientation of the top fiber and pull this laminate under inertial tension. Okay. So what we see here is pretty interesting, that as the top fiber orientation changes from 0 to 90 degree, the propagating crack path changes. So for all of these cases, crack starts at the notch tip, follows 45 degrees, so bottom fiber orientation, then reaches the interface, stays there for a little bit, but then goes up and then follows the top fiber orientation up until 45 degree cases. But when the fiber orientation on the top fiber becomes 60 degree, then it doesn't go to the 60 degree orientation. It just follows the lamination. Okay. And of course, corresponding behavior is pictured in the load displacement plot also. As you can see, the 45 degree has the most tactile response in terms of the failure displacement being the highest. And this one, 90 degree, 45 degree is the strongest one and the stiffest one, but brittler compared to the other cases. So if anyone is trying to design a composite where you want a predefined crack path, like this is the way you want the cracks to maneuver, you can probably use one such model fairly easily and then design, or basically design the layup, how you want your crack to propagate in a composite domain. So we extended our implementation for 3D geometry because that is where you basically exploit the entire loading spectrum for composite realistic applications. And we similar geometric and similar notch locations, but we tried different modes of fractures, different modes of external loading. And I'm going to show again few specific case studies. For more details. You are welcome to look at our recent papers. So in this particular slide, I'm showing you the case when the interface toughness is weaker than the bottom laminar toughness. And you see what is happening. The crack starts at the notch tip, the damage starts at the notch tip, but it does not propagate. Instead, another crack starts at the interfacial delamination, interfacial location, and the delamination continues to propagate. So delamination becomes the dominant failure mode. So if the interface toughness is weak, then you will always see delamination, at least under this uniaxial tensile loading condition. This is mode 1 loading, okay? However, if the interface is stronger, again, I showed you some results in the 2D case. We have done the same experiments in 3D, okay? And we have seen similar results that up until about 45 degree, it starts from the notch tip, follows the bottom fiber orientation, goes to the interface, remains there for a while, and then follows the top fiber orientation. But in 60 degree and 90 degree, it goes to the interface, then interfacial delamination is favored. And of course, these phenomena, the resulting phenomena that we are seeing is a competition between the individual toughness of the lamina and the toughness of the interface. Okay, so this is for other modes of fracture. So again, here the top and bottom fiber orientations are 45 degree. And what we are studying is that how the crack will propagate under different modes. And here, this one is particularly interesting. So what we saw for, this is mode 2. So in plane shear, what we saw, the fracture path depends on where the pre-notch is. If the pre-notch is at the mid-plane, where the interface is, then we see pure delamination. If the pre-notch is at an offset with respect to the interface, then we see an inclined crack propagation, and almost the way it doesn't even realize the presence of the fiber. So if it was pure matrix-driven crack propagation, you would have seen a crack path like this. Now, we don't know whether this is actually happening in experiments in all the cases, right? This requires rigorous experimental validation. We did some validation, and of course, depending on what type of fracture behavior is happening, our load displacement curve also shows significant change, which is quite expected. So for this is the part that we have already published, and if you just take a look at the quick summary of it, so the anisotropic regularization that we have introduced in the gradient term of the fracture energy works well to characterize this fiber-oriented crack growth, preferential crack growth. The homogenized constitutive framework was used to incorporate the elasticity. And of course, the regularized interface approximation works well to capture the delaminations. And we have done quite rigorous experimental validation in the papers. So I have showed you the OHT experiments before. We have done some of the interfacial delamination like the DCB or H-notch fracture experiments that has been reported in the literature, and our model prediction agree fairly well with the reported experiments. So these are the papers where you can get more details on this part of the work. Now I am going to switch and show you the recent modifications that we are thinking of doing. So this part of the work is not published yet, it's under review. So in this case, the first change that we are going to do is the constitutive description of the lamina. So instead of using that homogenized and axial stretch dependent behavior for the fiber kinematics, we are going to look into the more on an orthotropic sense of the constitutive behavior. This is what the composite community is bread and butter, right? So in a 2D, this is what the elasticity matrix looks like in the local material coordinates. So one is actually the longitudinal or the fiber direction, okay? And depending on the theta, you can do a very simple stress strain transformation to get the global stress strain equation in the Cartesian coordinate system. And that's what as I said, in the laminar theory, people keep doing. So in addition to that, to calculate the driving energy for the phase field crack growth, we did some modification. So what we are trying to say here is that we know that the crack propagates along the fiber direction, even under pure tension-dominated mode, okay? So if we think that the crack was to propagate under pure mode 1 situation, then from classical fracture mechanics concept, we know that the stress perpendicular to the crack path is responsible for driving the crack home. So from that concept, if the crack has to propagate longitudinally under mode 1, then the mode 1 driving energy should be dependent on the transverse stress. And we can just simply write down a strain energy density based on the transverse stress and the transverse modulus, like this. Okay. Similarly, if the crack, I don't know which one it is, but if it is to propagate under mode 2, then the shear stress and the corresponding shear modulus will be used to compute the shear stress, shear energy part, or the mode 2 energy part of the driving force, okay? And of course, we have to have these criteria to ensure that fracture happens only in tension-dominated situation. For the shear case, we depends on the principal stress calculation, that if our major principal stress is greater than 0, then it will be a non-zero term, otherwise it remains as 0. Okay, and correspondingly, we have the degradation in the elastic energy. So this compressive part is taken out from the total energy density. So this is what is important to note. It's not, as I said, it's not purely isotropic material like behavior, right? So just looking at the crack path, you cannot determine whether it's a mode 1 or mode 2 crack growth, right? You have to look into the stress, local stress, or the corresponding energy which is driving the crack growth to make sure whether it's a mode 1, mode 2, or a mixed mode situation. Okay. So with this, we went a little more ahead. Along with quasi-static fracture simulation, we wanted to see what happens in the dynamics. So if we have high rate loading, impact loading, which is what the composite people are often very interested in. So we basically implemented the system in the kinetic domain. So we have a kinetic energy term in the total energy of the system. So remember what we changed here, again, recap, that we did not introduce any anisotropic tensor in the description of the phase field fracture, which was done in the previous part of my work. Okay, that was not done. And we have a new history function because now we have two parts of the free energy or the elastic energy. One was mode 1 and mode 2. They are individually compared with respect to the two modes of fracture toughness to get the driving energy. Okay, so these were the changes that was done in the phase field setting of the work. So then, of course, we implemented, and I did not mention in the first part of the work, the numerical implementation still uses Abacus platform for the solver. So we write an user elements routine, and for the dynamics, we have used a numeric beta algorithm. And those of you who are familiar in phase field literature, we have used a staggered implementation. And I'm not going into the detail of the numerics here. The staggered implementation, basically, if you look at the whole potential, it's non-convex between U and D. So a global minimization is often very, very difficult to do, which is why we do the staggered implementation. Okay, so if there is interest, I can talk more about that. But then again, going back to the validation originally, so I'm referring to Professor Wass's work quite a bit in this talk, because that was our benchmark problem sort of thing, because all the material properties were listed in the papers. So it was very easy. So when we went to the orthotropic description of the lamina, then it was fairly easy to just straight away use their material constant. I did not have to do any calibration per se, except the two fracture toughnesses. Because those of you who are familiar again in the phase field literature, the fracture toughnesses, basically the Ambrosio-Tortelli type approximation that we are using in the regularization of the fracture term requires the fracture energy to be calibrated if we choose a specific length scale parameter. So either of them you can choose. So you can actually let the fracture parameter come from the experiments, and you can do a calibration on the LC. Okay, but then you have to control the mesh dependency there, because LC basically is used to resolve your crack surfaces, right? So it will depend on the mesh size. Okay, so here what we did is we fixed the LC depending on the mesh size. So if we have a fine enough mesh, then we can fix the LC and then we calibrate the two toughness. That's all. And once we have that, you can see our models are fairly accurate to predict the experimental response across the fiber orientation, and so do our predicted crack path. Matches with the experiments fairly nicely. Okay. So, and then as I was telling before, that we were doing a lot of dynamic events. So instead of pulling the weight specimen quasi-statically, we applied a high velocity impact. So it's an impulse. So 10 meter per second velocity was applied in 1 microsecond and then held it for a long time. So this is how the wave propagates across the domain. And what we see here, several different phenomena, that you see 4 cracks initiates from the whole edge, and all of them simultaneously propagates, and then there lots of branching starts happening, which is a very well-known phenomena in dynamic fracture behavior. If we look at the energy landscape locally, what was among those 2 modes of energy, which one was the driving force for this case? What we see is that in the crack initiation event, it was purely mode 2 driven energy. You see how high it is? So it was a shear driven crack growth, and that's what is happening in the 0 degree lamina, because it's the fiber matrix delamination that promotes the crack growth. Similarly, if we look at the branching events also, we see that it is mode 2 driven too. So these are some of the important velocities: trace wave velocities, longitudinal, shear wave, and the Rayleigh wave velocity, which we can use to compare certain quantities such as the propagating crack tip speed, etc. So same simulation, but 45 degree fiber orientation. Once again, we see the crack starts from the boundary, but quickly the crack emanating from the whole edge picks up, and you see the propagating wave front was not that homogeneous like the one we saw in 0 degree, which is quite expected because now the fibers are oriented at an off angle. It's 45 degree lamina, right? And if we look at the energy spectrum, we will see similar situation. So in this case, here it was mode 2 driven in the corner when it initiated, but at the whole edge, it was primarily a mode 1 driven crack. So it was essentially a matrix cracking along the fiber direction, parallel to the fiber direction. So if you compare the 0 versus 45 degree, you will see this one has 0 degree has way more branching, as you have observed. And that is quite expected because in that case, the impacting wave was propagating parallel in the fiber direction. So it was much faster and carrying a lot more energy. So it has a lot more energy to create more branching. Okay. So we continue to do.
Sorry. So this is a compressive wave that's coming down, right?
Yes.
And it turns around, and that's when you see the crack.
So yes. So when it goes here, yes, you see that the wave has reached around 5.6 seconds, but there was no crack growth around that point. So it goes and then comes back around this time period, and then you see now the crack initiates. Yeah, you are right. Yeah. So we continue doing this, and this is a Kalthoff-Winkler type geometry. This is a classical example of dynamic fracture in isotropic material. So here, the idea is that you have a specimen with 2 notches at one side, and then you impact again a compressive wave, high velocity impact in between these 2 notches. So for exploiting the symmetry, we just model half of it, and we consider different orientation of the fiber and see how the crack propagation changes. So again, for 0 degree case, we see that there is one single crack propagates horizontally. Okay. If we look at the energy spectrum or the local stress behavior, we will see that it is purely shear driven or mode 2 driven crack growth. So again, fiber matrix delamination, which is the dominant mechanism known to be for this 0 degree lamina. Okay. If we try to characterize the crack propagation velocity by tracking down as the tip moves, then we see that 5,000 meter per second is probably the stable crack growth velocity, which is like way higher than the shear wave speed in this particular composite. So yeah, we did not see any branching. Why I report here that we did not see any branching, because the moment we change the orientation to 90 degree, we see now the significant amount of branching happens as the crack tries to propagate horizontally. So again, same boundary conditions, only the fiber orientation is perpendicular now. Okay, so we see that the velocity of this horizontal crack tip has dropped down quite a bit compared to the 0 degree case. Branching tries to happen parallel to the fiber direction. And we saw precisely the first branching happened when the compressive wave went and came back to this point. You see here, this is the acceleration snapshot and the corresponding phase field evolution. So when the first wave hit here, we see a very minimal propagation as it continues to go. Remember, this part is purely shear driven. So the propagating wave is essentially a compression. Okay, so no normal crack, but shear. But then when it comes back, I will show you the energy spectrum now. So look at the element at the pre-notch tip and element at the first branch tip. And if you just look at this two energy plot, then you will see here it was more 2 driven at the beginning. As I said, it was shear driven. But when the reflected wave came back, we saw a mode 1 spike in the energy plot. And that is when we saw this vertical crack started propagating. Okay, first branch appeared. Just to give you a reference that in the literature, there has been quite a bit of experiments to do Kalthoff-Winkler experiments and simulation. So in an isotropic material, same boundary condition, same geometry, crack propagates in a pure shear driven like this. Okay, just to give you some inference to what happens in the regular isotropic geometry. So we continue and try to extract many different quantities. For example, I'll show here the global strain energy and the kinetic energy for the whole domain, not just locally at where the crack propagation is happening, but for the entire domain. And if we compare between 0 and 90 degree lamina, we see a very similar tendency that we have seen in the crack profile picture. So in 0 degree, faster wave propagation, so you see a very quick spike in the strain energy, and then it keeps on oscillating. Okay, whereas in the 90 degree, we see a very slow uprise, reaches fairly high value in the strain energy, and then it starts dropping. So 90 degree actually behaves like a more stable crack growth, as it is expected, because there are many branching happening. Every branching demands more energy. Okay, and of course, as the wave propagation perpendicular to the fiber direction is slow compared to 0, the strain energy takes much longer time to reach to this speed. Okay, so everything basically falls exactly the same conclusion that we are seeing in the crack propagation behavior also. So if we just look at more detail, so overall conclusion, it tells that 90 degree lamina basically shows or demonstrates more stable crack growth. If you compare with the quasi-static situations, I'm not sure if you paid enough attention, because I was just rushing through so quickly. In 90 degree lamina, quasi-static response was not that impressive though. 0 degree was much more stronger because we were pulling along the fiber direction, but it looks like in dynamics, it might behave little worse than 90 degree case. So again, we calculated the crack surface area. So it's in the phase field sense. Now the regularized crack surface and the propagation, the speed or the velocity of this crack surface evolution. Okay, so gamma dot. And for 0 and 90, if we compare, same story. 0 degree is much faster, okay, much quicker, okay, and much drastic. You see, it's like an unstable peak in the velocity and then it comes down. Okay, whereas in 90 degree, it's more stable, and these little spikes basically tells every time we see another branching appearing. Okay, so we can actually track down when the branching are happening just by looking at this velocity profile. Okay, so this was basically the comparative study of these two composites, and then we can even calculate the dynamic energy release rate again from the sense of Griffith. So we have all the energies and we can actually compute what's the dynamic energy release rate is going to look like. So this is the 0 degree and the 90 degree case. And as I mentioned before, again, if you see 0 degree spikes very quickly, comes down and then sort of like becomes stable. On the 90 degree, it was more oscillatory, much lower value. It doesn't gain as high as this one, but it was still showing some of this dip in the energy plot, which was corresponding to those branching events. Okay, so this, how much time we have? So I can probably 2 minutes. Okay, so we continue to do more experimental validation. So this is another experiment that we basically looked into. It was done by a group in Caltech, led by Professor Rosakis. Again, they have a laminate in one particular fiber orientation, and they hit it with a steel impactor on one side and monitor the crack propagation under symmetrically impacted and asymmetrically impacted specimen. And we saw that qualitatively the behavior match, even though currently our model do not show a very good prediction. And we have identified the reasons of not getting like quantitative prediction to be matched. One of them is like, of course, in the experiments, they have not reported multiple crackings. We are observing more than one single crack propagation. And remember, every crack basically demands some energy. So whatever we are tracking is getting distributed among these 3 branches in this case, but they have seen only one major crack propagation. We did not try to constrain the damage in anywhere in the domain, so that let the simulation do whatever it does and see where we stand in terms of prediction. So, and of course, there is a modeling going on also, not going on, published in 2003, where they have used elastic plastic constitutive description for the laminar level. If you remember, our constitutive description is purely linear elastic, so there is no dissipation because of the plasticity, which is probably another reason that we are seeing a little slower crack growth. We do not see why it should not work if we can probably constrain this part of the damage initiation. Probably we can get a better prediction. We have to work on that. I'm not claiming anything before doing that. So I will probably jump to the conclusions because I don't think we have enough time. So so the second part summary is basically we have used this 2D laminar level constitutive description combining with a new energy decomposition based on the local stress description to capture the anisotropic crack propagation. And in this case, we do not need to incorporate that anisotropy in the phase field regularization. So we can get rid of that anisotropic tensor and the scalar variable associated with it. We see that the dynamic crack propagation can be captured really well, which is inherently complex. As you can see, the crack path changes considerably from case to case basis, right? Which is a function of initial notch locations, applied loading, and fiber orientations. And I will leave it here, but there are some questions on this branching phenomena, whether what we are seeing is realistic or not. That's what we are focusing on. And I'll leave it up to here to just basically take any questions you have with this simulation on the Kalthoff-Winkler experiment. Thank you so much for giving me the opportunity to talk about this part of the experiment. Thanks. Thank you. So go ahead.
Question. So thank you for the work. Is the location of the branching events random, or is there something in the model that predicts where they appear?
So the model does not have anything to precisely mention where the branching will happen. The branching here is happening as you have enough energy to create another crack.
Okay.
So basically, if you see this phenomenon, you see here, so the bottom one is showing how the stress wave is propagating.
Right.
And that one is the crack. So when the wave starts, so when the wave comes, so that is when you hit, and this is the wave came. So crack starts horizontally. Okay.
So
you see that?
They look kind of random, right? Like,
yes.
Is there randomness built into this?
No, it's not built into this. I think it's the competition between the stored elastic energy at that local point and the impacting wave, which is the external energy that is carried by the wave. When they match the criteria of the fracture, it initiates at that point.
Gotcha, okay.
Yeah.
So then, when we, in experiment then, do
Right.
branching events correspond with any kind of like material properties, inhomogeneity?
Yes,
thickness,
so,
or anything?
so this is where I mentioned in the conclusion slide. So if you see, this is what we looked into also in the composite literature. Branching is rarely reported as an event, even in the dynamic fracture mechanics. And they say, because here, even though I have the constitutive anisotropy, I don't have any micromechanics. For example, individual fibers are not modeled, right?
Okay.
Neither the matrix. So I have still a homogenized continuum. Well, this continuum has different elastic property in different direction. But they do not represent single fiber or the fiber distributions and the matrix around them.
Okay.
That's not there in the present setup. In the real composite, what we envision is that because you have this microstructure, the microstructure will govern how the crack will propagate. And in many cases, we do not anticipate any branching, which is why experiments also do not see any branching. Because fibers, depending on the fiber volume fraction, they're like very close contact with each other.
Alright.
So you probably do not have enough room. So once you have a fiber matrix interface debonding, which we are seeing, it will probably continue to grow along this direction because that is the weakest path or favorable path for the crack to propagate, rather than trying to find another weakest part where the energy competition is getting met.
Mhm.
It will probably not happen if we have the microstructure built in inside the constitutive description.
Alright, I'm with you. Alright, thank you.
Go ahead.
So for the dynamic problem, you were saying there is no inherent randomness to the model, right?
Inherent
Randomness
randomness to the
to
model.
the
No.
model.
Yes.
Does that mean if I run the same simulation over and over again, I'll
Right.
get the same exact crack paths?
Yes.
Or that will
That won't change. No.
that won't change?
That won't
The
change.
problem doesn't have any.
If you have exact same boundary conditions, exact same property,
It will be the.
Yeah.
Okay.
shouldn't. Because again, if you look at our numerics, which is, of course, this part of the paper is not published. We are just addressing the reviewers now. Hopefully it comes within coming months or so. But if you see so you have to make sure, because these fracture events are time sensitive. So you have to choose extremely small time increments so that you do not miss all these events. So as long as you stick to whatever we are doing, it should not change.
It's like repeatable.
It's repeatable. Yeah.
Okay. Could you go back to slide number 23? I think probably that
Sure.
was a study part.
Slide 23, right? Let me go out of this video.
Yeah, so I was trying to understand what does it mean model versus experiment for matrix cracking fiber matrix.
Oh, okay.
Yeah.
Yeah, so
How do you?
very good question. I didn't show you the result. I mean, where we got this one from. So basically, if we again remember for each dynamic case, I was showing you the local energy spectrum. So if you just go, and I don't have the plot here, if you just go and look at the energy spectrum locally, you will see for this case, it is the psi1 or the mode 1 energy that is driving the crack. And if it is psi1, that means it is essentially the matrix cracking that is happening. As similarly, in this case, on the 0 degree case, if I look at the local energy, then I see it is the psi2, which is basically the fiber matrix debonding. That is the micromechanics. So what I am trying to say here is basically for this approach, you not only know the crack path or the load displacement curve, you also know the underlying mechanism. Of course, in OHT, you know what's the underlying mechanism because this is simple. But for many dynamic cases, just looking at the crack profile, you probably don't know what mechanism performed the failure or the crack path. But if you look at the energy spectrum locally, you will know what was it mode 2, was it mode 1, or was it a mixed mode scenario. You can.
One more question. Can
Yeah, please. I have no problem as long as.
So you showed us the results where you had the notch, which was parallel to the interface.
Yes.
can we get some insight if the notch is oblique, right?
I actually have a,
Your simulations can
right.
predict what happens, how
Yes.
the crack growth will look like.
so in this paper, I don't have the slides for that, I'm sorry, but
Yeah.
we in this paper,
Okay.
we have done many other parametric studies.
Okay.
So you can actually look into that. We actually did a perpendicular orientation, changing the fiber orientation, etc. Yeah.
Okay, thank you.
Go ahead.
Peter, and then go ahead, Peter.
Well, so I work on the bio side with Ellen, so I'm kind of thinking about this in the context of BACL, and that lamina to me reminds me of the interface between the two bundles that make up the ACL. Is this mathematical framework reliant on that interface being planar, or could you introduce some tortuosity?
In the interface?
Yes, for the interface.
In theory, it should be possible. All you require is a smooth functional representation based on your coordinates,
Okay.
right? But I have not done how in theory, it's fairly easy. All you are just doing is a sharp function, you are approximating like a smooth distribution, like an exponential type of function, right? But I don't know how critical it will be in terms of the numerical implementation. Don't anticipate any big problem as long as it is not evolving. So if it is just a space-dependent thing and you solve it just once at a time, then you should be okay.
And has anybody ever done a hierarchical approach where the fibers at the bottom are itself a composite?
Yeah, there is a group in Oxford. They actually looked into the not as detailed as we are doing, like the approximating the sharp interface and then the interfacial displacement jump, what we have shown here. But they are looking at the micromechanics, like the individual fibers and the matrix, and they have pretty cool videos. I have seen their website that's showing the crack is basically covering the tortuous path around the fiber, etc. But they don't have any precise interfacial modeling. I don't think so. So far, what I looked into them.
Interesting.
Yeah.
Thank you.
Yeah, I just have a pretty basic question. So
Sure.
if I actually have the material, does each fiber just goes from one end of the material and reach the other end? Like it's just one string, or is it a lot of
Yes.
rods?
So the experiments that Professor Vasi's group were doing, and our assumptions of this lamina, where is that? Yeah. So this one, for example, they had the laminas were oriented through the width of this sample. Okay.
So
45
it's just like one long string,
Going from one end to the other.
Continuous.
Yeah, continuous.
and they don't twist up or doing something.
So there are other microstructures available in composites. So they do weaving, they do twisting. Pre-twisted fibers are introduced to give more strength in the composite. So those are very complex microstructures.
But in this case, you can just look at the cross section and they will
They will have,
you.
yes, they will have, I think I have a schematic here, but they actually look like fairly like this. If you look at the cross section, this is how it will look like. So it's like those dots are the fibers.
I see. And the volume fraction you're interested in is 0.6.
So that was the volume fraction reported 0.6, which one? Oh, okay, in the constitutive
Yes,
description.
all that in-
Somewhere in the table, yes. I think that was reported in this one. For this one, I think this one was just our parametric studies. Because if I remember correctly, Tony's paper had a little higher volume fraction. I don't exactly remember the data. Yeah, this one was just on the parametric study, but you can, for the first part of the model, you can actually choose the volume fraction for your actual sample. If you know the volume fraction of the fiber, you can calibrate that because our free energy is expressed in terms of volume fraction, so it's a parameter in the model.
I see. Okay, thank you.
Sorry. Go ahead.
Yeah, so you use the sort of smoothing method to smooth the crack itself and also the interface between the different layers or lamina
Right.
of the composite. Could you use that sort of method to to apply it to between the discontinuities between the fiber and the matrix.
Yes.
I assume there is some sort of discontinuity.
Yes, because the material properties are so distinctly different. Yes,
Right.
you can do that, but imagine that around each fiber, if you define the interface, it will be computationally extensive to capture that thing. But it can be, in theoretically, it can be possible. And we did some simulations. This first part of the work, the student has graduated now. In his thesis, he has shown that we can actually model these things. It's a cool simulation to see if you have like still countable number of fibers and around the fiber it still models a homogenized or regularized interface, you can actually do that. But if the numbers are huge, which is in reality, you have 60% of fibers and around each fiber, if you numerically model the interface, it's not going to be that easy to handle the data and the simulation itself.
Thanks. Thank you.
Yeah.
I just have a question. So here in the standard phase field model, the length scale will modulate the toughness and the strength.
So, right.
So if you have direction dependent strength,
Right.
but then you're fixing the length scale depending on your element size, how do you get the
Very good question.
experiment?
So what we did here so far is, I would say it's little crude in the sense exactly on the idea of 81 calibration.
Mhm.
So for this particular presentation, we made sure that along the crack path, the mesh is uniform in size for these three devices. So you have enough small mesh size so that HE for across these three specimens are same, the smallest element. Then we had an advantage of choosing the LC as a constant across these three specimens.
But then you fix the strength.
Yes, but then I fixed the strength, which is why I had to calibrate both this fracture energy.
Oh, okay.
This
So you're matching the strength and then
Yes.
you're changing GC to match the
To match this, yes, strength, yeah. And
To match.
that is why you will see
Mhm.
I get one very good approximation, but these two are not matching on top of each other.
Even if the strength matches.
It just shifts, yeah, the activity shifts, yeah. So this is what one of the question the reviewer has asked. Can you do a little more, better control in here?
So
But if we just stick on 81, we cannot.
yeah.
That's the inherent limitation of this.
There is a way if you can incorporate this into your free energy as a parameter to make the simulation length scale insensitive.
Right, yeah.
But this results in a different model.
That's what I was thinking.
Yeah.
I mean, yeah, so that's our plan, but it has to be another whole
It becomes a whole new model.
new model. Like, we have to test the whole thing again for that.
Yeah.
That's what I was trying to avoid the reviewer by saying that we will do it in future sometime.
Thanks.
Yeah. Yes.
All right, well, thanks again.
Thank you. Thank you very much. Thanks for coming, everybody. Oh, okay. Sure. So I will just put this thing here so that I don't forget and say.
So, I'm wondering if you try to see how other approaches work there, because this is interesting. You're picking up my nose job, obviously.
Yes.
But then there's the slump valleys
Yes.
again.
Yeah.
And yeah, you're trying
So
a little bit.
Yeah.
But then it's coming
Again,
down again,
yeah.
and then there's a little bit of a shoulder.
Oh, yeah.
There's a lot of detail that you're picking up.
Right.
there. So I'm wondering how would like a cohesive zone work? In this case, would it get that kind of detail? How would the?
Yeah. So
Like, have you
Tony's
ever-
paper, they have used some
Yeah.
cohesive zone model on this
Oh.
data too. But yeah, it's not. You can see in his paper, it's not. I don't know if Tony sees ever. Oh, sorry, you want to see this, right?
Oh, no, this is.
Yeah. So yeah, it's not easy to get those many details.
Yeah,
It's not.
no, I think that's pretty good.
Yeah.
Yeah.
I just wanted to say hi. I work with Professor Was.
Oh,
I
okay.
emailed you a couple of times
Yes.
when he was in India.
I think even this time Tony said that he will be attending the talk. He emailed me.
Oh, okay.
He emailed me. Yeah. When I think when he saw the announcement probably.
By the way,
Nice to
I'm
meet
also
you.
from IIC.
Yes, he told me, I think. Yeah.
I've done my master's from IIC.
Which department you were?
Mechanical.
Who you were working with?
I was working with, I don't know whether you'll know him because when I
New professor?
joined, when I joined, he also joined. So I
Oh.
spoke to Mr. Nagarajan.
Group meeting.
Okay, I know.
But you would probably
Yeah, I worked with him.
So-
I worked
Oh, you-
with Professor Narasimhan. Yeah.
Oh, you did PhD from Professor Narasimhan.
Yeah.
Randy.
I know.
Yeah. They have
Then you must be knowing Joe.
job. Yeah. I mean, I took continuum mechanics.
Yeah, that was a tough course.
Yeah, very horrible experience during that time. Somehow I got B. I can share it with you.
Oh, okay.
Yeah, but it was
She's gonna
very
come
tough.
up
Yeah.
and
No, I